Hey, what's up YouTube? I hope you're doing well. In today's video, I'm first going to demo a new blueprint tool I just released on my Patreon, and then I'll show a bit of its inner workings. Before going any further though, a bit of context. I've been spending time recently getting myself up to speed on some UE5 features I haven't had the chance to experiment with yet, namely PCG, geometry scripting, and scriptable tools. So I wanted to find myself a project I could use as a sort of sandbox to create a bunch of random tech tools, kinda like what I did with my desert scene project in a way. And I somewhat randomly decided to go for an ice cave, why not? I still have to do a breakdown of that ice shader of mine anyway, so I might as well kill two birds with one stone. And I guess this blueprint tool and this video is the first thing that comes out of this initiative. That being said, that tool is still entirely made using vanilla blueprints, so not really using those new fancy UE5 features I'm trying to learn, but I promise I got cool things coming your way. Anyway, creating a cool looking ice shader for just one isolated rock is plenty doable. Creating a cool looking ice cavern is another thing entirely. That's where complex light scattering comes into play to give life to the super thick ice, right? And where typical methods to approximate this behavior, like subsurface scattering, show their limits. One solution can be to create a new shader model that can sample the baked volumetric light map, exactly like what they did on Gears 5. That however requires diving deeper into the engine than I'd like to at the moment, plus is a technique inherently limited by the volumetric light map's own limitations, resolution, the way it's authored, baked, and so on. So I wanted to see if I could create a similar solution, but one that does not rely on volumetric light maps and a custom shader. And this blueprint is what came out of this attempt. It's not perfect, but what is. So without further ado, let's see what it's capable of and how to use it. So here I have quite a basic ice cavern, and with this tool I'm going to paint light in a volume texture to approximate how light scatters in the ice. Now I said approximate for the lack of a better word, because it's really a gross approximation. Do not expect anything physically based, right? At this point it's entirely artistic, but it somewhat gets the job done. Okay, first things first, I'm going to drag that BP volumetrics actor into the scene and scale it up to more or less match that ice cavern's overall size. Next, it should already point to an existing volume render target, but if not, create one and set it here. It likely needs to be HDR for this tool to properly work, so keep that in mind. Next, I can enable a debug view and display each voxel in that volume texture. And finally, I can set that volume texture's resolution in X and Y and Z. Keep in mind that this is a blueprint tool, and despite it being an offline tool, performance can be a concern, as you'll see in a minute. It can be a bit slow to do its thing, so don't go crazy with that resolution. If you need to cover a large area or need a decent resolution, I suppose either split that area into smaller areas with multiple volume textures or convert this tool to C++. Anyway, having done that, I'm going to run this editor utility widget. It should automatically pick up that volumetrics actor, and in case it doesn't, or you have multiple ones in your scene, use that selection box to select the desired one. And really, all you got to do is press bake. Well, yes and no. It baked with success, but for now there's nothing to bake. For this I created what I called jobs. A job is an actor I can drag into the scene to paint voxels in all sorts of ways. I've made a bunch, but you can build your own. I provided a template that should indicate quite clearly how to proceed to create your own. Plus these existing ones serve as examples, I suppose. Anyway, let's use, say, that color plane. Simply drag it in the scene and press bake. That job is automatically picked up by the tool and voxels are now white. That's because this specific job simply applies a given color to all voxels, and for now that color is, well, white. Change this to, say, red, and voxels are indeed all red, which means that this volume texture is entirely red, right? Next, that job has this color mode setting I'll explain later on. Then you can specify that job's name. It doesn't serve much purpose besides being printed in the log though. Priority can be used to ensure that a job is performed before or after another one. Alpha is simply how much of that job is applied in a 0 to 1 range. Mode is kinda cool and lets you use an iterative workflow. To demonstrate this, let's drag this color radial job into the scene. I'm going to tweak its radius and change its color to red as well. Then I'm going to set its mode to subtractive. Finally, I'm going to make sure it's processed after that first job by setting a lower priority. Press bake, see, All voxels are red except those within that radius, where that same red color was subtracted. So you can play with an additive mode, subtractive, multiply, divide and replace. It should sound quite straightforward. Moving on, let's get rid of those two jobs and check the color linear one. It's once again pretty simple, it creates a linear gradient in 3D space from point A to B. And that box one is similar, right? Along with that mode, you can also use masks. To demonstrate this, let's again make use of that plain color job. Now I created two masks, a box and a sphere, but again you can create your own and use the provided template to see how to do so. Anyway, let's use a box mask, move it here and maybe scale it up a bit. Now specify that box mask actor in that job and bake again. See, that job no longer affects any voxel within that box. So that, coupled with modes, should let you have complete control over the bake process. Moving on, I included a bunch of other jobs. There's a blur, and it does just that, it blurs voxels. It's by far the most expensive one to compute, see, it takes a bit longer to bake. Anyway, there's also a directional light. This one simply does a bunch of line traces from a given light direction towards each voxel. This way you can create an ultra basic volumetric shadow map. That other job is to colorize voxels all around the 3D grid. That can help prevent bleeding artifacts from one edge to the other when sampling the volume texture, right? It's a bit of a sketchy hack, but oh well. Next, random, it does just that, it writes a random color per channel in a given range. And finally, thickness, that's the most sketchy one. It does a line trace from each voxel towards the light, and from the light towards the same voxel, in a very crude attempt at finding the thickness of whatever object is blocking the light, if any. And that's pretty much it. With these tools, you can literally paint light in a volume. Once baked, that render target volume can be sampled in a material quite easily using this included material function. It needs a volumetric texture. Note that you may use that volume render target to see updates live when baking, but once you're satisfied with it, you really should create a static volume texture and use that one instead. Anyway, that material function also needs two vectors to correctly project that volume texture in world space. An origin, where that 3D grid is located in world space, and that 3D grid's XYZ bounds. Both, by the way, are provided upon bake completion. Then specify a step distance in centimeters and the amount of steps to perform. Plug that into the emissive and you should be good to go. For this particular example, I used a bunch of radial gradients, one here, and one there, all in additive mode, plus a directional light and a thickness as well. Again, the idea behind this tool is not to create something physically based or detailed. It's meant to create artistic driven color gradients and give the impression of something that happens underneath the surface, right? And because I wanted to keep both the volume texture size very low and only do a couple of ray marching steps in the shader to maintain decent performance, I had to skip the usual ray marching techniques. Meaning usually you have some kind of volume quite well defined with a proper volume texture or distance field or mathematically, and you only march forward as far as you can go within that volume to accumulate samples or data if you will, and then you stop. Here, because the volume is so poorly detailed due to a super low resolution, I can't really do that. For instance, see that ice pillar? There are so few voxels here that I wouldn't be able to properly detect where a ray enters and exits it. It's like I don't have enough resolution in that volume texture to properly describe smaller shapes. Thus I'm kinda blind when ray marching in it. So I took a very naive approach, which is to keep marching forward for a given number of steps and that's it. Hence why, despite voxels all around this pillar being black, I still get to see some form of lighting when looking through it in that direction, because rays go past it and reach that area where there's some lighting baked in those voxels. Also keep in mind the step distance and the amount of steps allow that to happen, right? If rays can travel far enough to reach those voxels, well, no light shines through that pillar anymore. So actually, the more steps you take, the brighter it gets, because it keeps accumulating samples. That's why I said earlier that this is a gross approximation. This is by no means physically based, yet it somewhat works, right? This is without and this is with. The difference is quite noticeable, and I can very easily tweak things to my likings. It's quite an artistic workflow. Anyway, moving on. At one point I realized I could bake vectors as well as colors, because an RGB color could be interpreted as an XYZ vector, right? So this tool also allows you to bake 3D flow maps. It's quite simple. Instead of painting arbitrary colors, paint XYZ directions using the red, green and blue channels. And to make this process easier, there's this option built in most of these quote-unquote color jobs. That color can be user set, or it can come from that actor's forward vector. And that's it, that RGB volume texture can now be a 3D flow map. Quite cool. Not only that, but it can also pack an extra value in the alpha channel. So what I ended up doing was bake a 3D flow map in RGB and some form of light scattering value in the alpha channel. That alpha channel is sampled in the ice material, right, to add some emissive color, and the RGB channels are sampled in that Niagara particle system to add some XYZ forces. And that's pretty much it. That's my attempt at building a custom solution entirely built using blueprints to paint 3D flow maps and volumetric textures. Now let's get technical and see how it was built. It all starts with this editor utility widget. This is a special kind of widget that can be called in editor. Now technically this tool doesn't need to go through an editor utility widget. The only reason I'm using such widget, well, two reasons actually. One is to be able to tick an actor in editor. That's usually my go-to strategy when I have a blueprint tool that does heavy computation and that would make the editor unresponsive for a while. To provide a much better user experience, I spread that workload over many frames to avoid an unpleasant chug. And that way I can also provide a progress bar and a log, which is the second reason I'm using an editor utility widget. It's a bit more user-friendly to have a tool that has its own log than to go look for some info somewhere in Unreal Engine's log. Now this editor utility widget doesn't do much on its own. I use single property views to create two properties, and I explain in details in a previous video how to use them, so feel free to check it out. In a nutshell, just have to call this and make that single property view point to an existing variable, and that's it. Moving on construct, I first try to get a volumetric actor. First, by checking if one is currently selected in the world. Second, via get all actors of class node to try and get the first one that exists in the world. If one is selected or if one exists, I cache a reference to it and bind all its event dispatchers. It has a few and I'll go over those in more details later on. Each event is bound to one of these utility widgets function. For instance, let's assume the bake has started. I make that widget switcher switch index and make that progression box visible. This makes that cancel text and progress bar be visible during the bake. On bake progression, I just update the progress bar size and text. And on bake ended, I merely hide the progress bar and make that button show this bake text again. Nothing fancy, to be honest. Same for export started and ended, it's really just cosmetic and making sure buttons show the correct text or are not clickable depending on what's going on during the entire bake process. Then on destruct, just to be on the safe side, I unbind those same event dispatchers and clear the reference to that actor. Next I have this bake button that calls this actor's activate and deactivate functions depending on its state, to start a bake or cancel an ongoing one, right? And if baking, forward that editor utility widget stick to that actor. That's how I make an actor tick in editor, right? By using an editor utility widget stick. There are other ways, but I think that you have to use C++, but don't quote me on that. Anyway, that widget also has this log feature. You see that actor broadcasts an event dispatcher to send dialogues text and type. This widget listens to this event and adds any log received that way to its logs array. And if this logs type isn't currently filtered out, construct a text and add it to that scroll box right away. There's also this clear logs button that calls this, clear logs function. It simply clears the scroll box children and that array as well. Also, when that enum used to filter logs is changed, maybe the user wants to check for warnings or something, clear children loops through that logs array again and add all logs matching this new filter. And that's pretty much it for this widget. To summarize, it gets the volumetric actor to receive messages this actor broadcasts, messages used to update buttons, text and the progress bar. That widget has a button so the user can start a bake or cancel an ongoing one, and that widget stick is forwarded to that volumetric actor during a bake. Voila, most of the logic then happens in that volumetric actor, so let's check it out. It's a bit more beefy, but nothing too crazy either, bear with me. Alright, this actor has a single vector4 array that contains all Voxels RGBA values. Now, quite recently I released on my YouTube channel a video and a project on my Patreon showcasing a technique to convert a one-dimensional array into a 3D one. Here I use the same exact technique to achieve this. Feel free to give that video a watch because I won't explain this technique again in details here. The gist of it is that this one-dimensional array contains all grid cell indexes, and there's a method to convert a voxels index in that one-dimensional array into an XYZ grid index, and thus, using these 3D grids origin and bounds, into an XYZ world position in 3D space. So first things first, get that grid's origin and bounds. That happens upon the tool being activated. There's this initiate tool function which, initiates a couple of things and does a few sanity checks. Make sure the voxel count is not null, then make sure the volume render target is valid, and resize it to match this 3D grid's resolution. That 3D grid's bound is then simply computed from a box component attached to this actor, so make sure its bounds are valid as well. Next, cache all these values, resize the voxel array to match the voxel count, which really is just that 3D grid's resolution in X, Y and Z multiplied together. Batch is a special thing I'll explain in a minute. Once that's successfully done, the tool is now considered active and the bake can start. But first double check it has not already started for some reason. Then gather jobs to bake, so I use a getAllActors of class node to get all blueprints that are a child of this blueprint class. And you guessed it, all these jobs I demonstrated earlier are child of that class. It provides a few functions, but more on that in a minute, and also has a few variables common to all jobs, name, priority and so on. Once jobs are gathered, they are sorted by priority, and a simple while loop does the trick. For each job to sort, find the one that has the highest priority, then add it to the jobs sorted list, and remove it from the jobs to sort list. Rinse and repeat until there's no job to sort anymore. And that's the list of jobs to apply sorted by priority. At that point the bake can start, so broadcast that event and that function returns true, which makes this function return true as well. Okay, so at this point the tool is now considered as active, which makes this function be called on tick. It's for now baking, so update bake is called. This function gets the first job to apply. If there's none, bake is ended and the tool moves on to its export state. More on that in a second. However, if there is a job to apply still, apply it. So forward self, so this job actor has an easy way to access these volumetric actors' public functions and variables, right? Like those getVoxels and getBatch functions. Time to explain that batch thingy then, I suppose. Well, let's assume this 3D grid is 16 by 16 by 16. That's a tiny volume texture, but that's already 4K voxels. And a 4K for loop in Blueprint, it can chug quite hard, depending on what you do in that for loop. So the purpose of this batch thingy is to only process a handful of voxels at a time. Let's say the first 200 voxels the first frame, next frame the next 200, and so on and so on. You get the idea. So this batch variable is just an endpoint. It really just is a start and an end index in that voxel array to create a range of voxels to process this frame, if that makes sense. Concretely, once a job is applied, this batch is incremented by this setting. Right now, the volumetric tool is set to process 500 voxels per frame. Why 500? Well, why not? It's quite an arbitrary setting, to be honest, so feel free to tweak this to your likings. There's nothing preventing you from setting this variable to, say, 10k and process every single voxel in one frame. It's just going to chug hard, nothing dramatic. Anyway, if the start index of that incremented batch exceeds the amount of voxels, well, it means this job has been applied to all voxels, so the batch is reset and we can move on to the next job, if any. Else, it's sanitized, meaning I ensure it never exceeds the amount of voxels and that the start and end indexes are indeed a start and an end. It's really just a security measure. That means that if not all voxels were processed for this job, well, just broadcast an update event and wait for the next batch to be processed next tick. Else we are done with this job, so it's removed from the list of jobs to apply, and next tick, rinse and repeat, and that's it. Eventually the tool will have completed all jobs, so that array will be empty and the bake will end. Now, what actually happens when the job is applied? Well, this function in the job parent class doesn't do much, as you can see. This function is meant to be overridden by child blueprints to implement the desired logic. So let's check, say, that color radial job. First, if that job's alpha is null, there's probably no point in looping through all voxels, so return false right away, so that job can be skipped entirely. But if not, get the list of voxels to mask out. I'll get back to that function in a second. Next, loop through all voxels in the current batch. For each, check if that voxel is masked, and if not, using a technique I described in a previous video, I can convert that voxel's linear index into a 3D world position. Thus, it's just a matter of getting this voxel's world position and doing some kind of logic with it. Here, this particular job is meant to be a sort of spherical mask, right? So just do a 3D distance check to compute a 0 to 1 opacity value. Opacity value then used to drive how much this color is applied on top of this voxel's current color, which is, by the way, done differently depending on this job's mode. Additive, subtractive, multiply, you get the idea. It then calls this volumetric actor's setVoxel function, which does just that. It updates that voxel array at a given index with a new RGBA color. So that's the idea. It's probably a lot to digest, but I'm doing my best to explain this. Now, when it comes to masking, that job parent class comes with a function that loops through that job's mask actors list to build a set of indexes to exclude. It does this by calling this mask actors parent class function, which is empty here, because this function is again meant to be overridden in child blueprints. So let's check, say, that sphere mask. It's overall quite similar to a job, meaning it loops through all voxels to bake this current batch, converts a voxel linear index into a 3D world position, and based on its position, checks if this voxel should be masked or not. Meaning, for a sphere mask, is it in this sphere? And for a box mask, well, is it in this box? You get the idea. That function thus outputs a set of voxel indexes to mask out, set that is iterated on using a union to combine multiple masks together. That's the bake process in a nutshell. Oof, that's quite a lot. So let's summarize. That widget calls this actor's activate function. Upon activation, some sanity checks are performed and jobs are gathered and sorted by priority. Once activated, this actor can tick in editor because of that editor utility widget's tick. On tick then, it gets the first job to apply and calls this apply function on a first batch of voxels. If applied, increment that batch variable so that next tick this apply function is called on a second batch of voxels, on and on until all voxels are processed. When that happens, the tool moves on to the next job. Rinse and repeat until there's no job left to apply. Cool, at this point the bake is complete, so that export state starts. It's one thing to write RGBA values in this array, but it still needs to be written in a volume texture. And sadly, blueprints do not offer any method to write into a volume render target. There are workarounds though. You could use a 2D render target and build a pseudo volume texture, but that's annoying to do and not a great user experience. Niagara to the rescue then. See, this actor has an export to RVT Niagara system. And when that export state starts, I forward that voxel array to this Niagara system. I also forward the render target to write into and the grid's XYZ resolution. Those all are Niagara user parameters, thus can be set via blueprint, right? So I used a GPU emitter with a single simulation stage. That simulation stage iterates on this 3D resolution, I may say. So assuming 16 by 16 by 16, this would be called 4K times. In that simulation stage, using a custom module, I get that voxel vector for array and get the value at the execution index. Value written into that volume render target at an XYZ pixel coordinate derived from that execution index as well. And that simulation stage is on during one single frame because its enable state is bound to that boolean, which is only true for one single frame. See, export starts, it's set to true. Next frame that actor is ticked, and during export update I call export end, which sets this boolean back to false, and voila, that render target now contains those RGBA values. Last thing I want to explain, the ray marching shader. It uses a custom HLSL node, but nothing too crazy. So first order of business, transform that pixel position from world space to that grid space using that grid's origin and bounds. So in a nutshell, it's made relative to the grid's origin, then converted to a 0 to 1 UVW space based on the grid's bounds. Keep in mind that this grid is assumed to always be aligned with the world XYZ axis. Next, the step distance is multiplied by the negative camera vector to march away from the camera, right? And divided by the grid's bounds to convert it from centimeters to a 0 to 1 UVW space. Next, sample the volume texture, accumulate samples, march forward and make sure to exit if the next position is out of the volume texture, else rinse and repeat, and voila, there's not much more to it really. And that's how I built this blueprint tool in a nutshell. I left out some tiny details, like the debug view, which uses a second Niagara particle system, but I'll let you check the project files in case you want to see more. Files are available as a tier 3 reward on my Patreon. That's it, I hope you found the video useful, feel free to like the video if you did, and subscribe to the channel. I'll keep working on this ice cave project and hopefully build some more cool tech to show you guys, so stay tuned. In the meantime, thanks so much for watching and thanks so much for the support. Take care of yourself and I'll see you in the next video. Bye bye!